Hello, today I hope to show you a useful tip for the FMA exam through two of the problems, both from 2017 and then one from more recent one, 2018. They both use the same idea about parallel series strings, splitting strings, and splitting springs and having springs on two sides of an object. So first, this is number 16 from the 2012 FMA exam. It says, inside a cart that is accelerating horizontally at acceleration A, there's a block of mass m connected to two light force constants, K1 and K2. Block can move without friction horizontally. Find the vibration frequency of the block. Now if there's one spring here and the other spring here, you might be confused as to how it interacts with both of them, because if it gets pulled one way, then it'll get pulled back the other way, right? So how would you even go about finding the angular frequency around that? Well, you might need to rephrase this problem. Now, imagine you take the spring over here and you move it over here. So now you see it like this. Well, now you see two parallel springs right here. I guess something I forgot to mention here was horizontally at acceleration A. Well, if you've done mass spring problems, you know that if you rest it up here, it has a constant acceleration of gravity down. But the frequency doesn't change even if you didn't have it, because the frequency is only dependent on K and M. So, okay, what do we do with this then? Well, the spring constants are K1 and K2, so just say the top one is K1, bottom one is K2. Okay, so I'm going to take a detour and point you towards two equations. One is for series springs, and one is for parallel springs. So if you're familiar with capacitors or resistors in circuits, this is pretty much the same. You can have two individual, or more than two individual springs, and then you can use that to calculate an equivalent spring just as a single one, so it's easier to use for equations. So for this, we have two parallel springs. Okay, so let's take K1 plus K2, so that's the same as whatever we need for an equivalent spring, and then at the angular frequency, we take K1 plus K2 over, and then M, just the mass of the block. So that's what we get for W, and then if you want to find F, the actual frequency, we take 1 over 2 pi, and then we multiply by that. There we go, and let's see which one this is the same as. See, it is E. Now with process of elimination, we're sure it's not C or A, because acceleration, it does not affect the frequency, and it wouldn't be the difference, because that's not how springs interact with each other. So we would consider B and E, and then if you know this, that this is equivalent to a parallel, and you use this equation, then you'll pretty easily find its E. Okay, so here we have the second problem. This one is a light uniform ideal spring is fixed at one end. If a mass is attached to the other end, the system oscillates with an angular frequency. Now, if the spring is fixed at the other end, then cut in half, the mass is attached between the two half springs. The new angular frequency of oscillations is... Okay, so this will need me to bring up a second concept, which is what happens when you split a spring in half and then you use it. Because as far as we know, this should be the same as by the previous problem, as one spring here, another spring there, holding the ball. Two parallel springs. So we should add whatever this is, K something, K question. They should both be the same because, well, when you cut it in half, getting this would be the same as getting the other half. There's no difference. Let's try to find out what happens when you split a spring. Well, remember the series equation? 1 over the equivalent spring constant equals 1 over first spring constant plus 1 over the second spring constant. Now, how do we find what we'll say that this entire spring is a spring constant of K? So that means that's what the equivalent thing is, 1 over K. And we want to find out what each of these little I called them Ks for K short. Let's find the spring constants of those. So we have 1 over K equals 1 over Ks plus 1 over Ks, or 2 over Ks. After doing this, we get Ks equals 2K. Now, this is already an important thing to know. If you split a string in half, or a spring in half, the equivalent spring will have twice the spring constant, which makes sense. If you cut a spring in half, it's harder for you to pull it as much. It requires more force. Okay, so now that we know Ks, let's use the parallel equation and plug it in for these. So the final equivalent spring, KEQ, is Ks plus Ks. And that means that the equivalent spring. Now that we know it's 4K, let's try to find the ratio from the original angular frequency to the new angular frequency. So the original one would have been W equals square root of K over M. Then find the new equals 4K over M. Let me take the square root of that. And that just equals 2 square root of K over M. Now you see where I'm going with this? Replace the square root of K over M with omega and we get 2 omega. There we go. Got D 2 omega as the answer. Hopefully those two examples showed off this tip. It shows up a lot in FMA. Hopefully I showed that. Yeah. Use this. Move it to the other side ability to your advantage in your next FMA exam. Alright, see ya.